Hi, everybody. Today we are going to talk about layout generation and our new approach, which is called DLT, to solving this task. So what is layout generation? Layout generation refers to the task of placing and sizing visual components on a canvas. And well-designed layouts allow users to quickly understand and efficiently control the visual design. Therefore, layout generation is a crucial aspect of graphic design. In many practical applications, we want to be able to control the layout generation. We would like to allow our users to fix certain attributes of the components, such as their class or position, and then generate the remaining ones, like the component size. Another option that we would like is to fix some portion of the components and use layout generation to complete the layout. This ability to condition layout generation on a partial subset of component attributes is critical to real-world applications that involve user interaction. Let's double-click on how layouts are represented. Layouts are often represented as a set of components, each consisting of several attributes. Previous works typically consider several common attributes, such as class, position, and size. But it's worth mentioning that in practice, there are many more layout attributes to consider, like color or the content itself. So the question is how to apply a generative model to the natural representation of layouts. One option is to use a transformer-based model where the attribute of components are mapped to discrete tokens. However, using discrete tokens fails to take into account the natural representation of the data, which includes not only discrete features like the component type, but also continuous features like the component size or position. Another popular approach is to use diffusion models. Recently, diffusion models have shown remarkable generative capabilities in various domains like text-to-image and video generation. However, it is unclear how to apply diffusion models to the natural representation of layouts, which consists of a mix of discrete attributes and continuous ones. To address this limitation, we introduce a new framework, a diffusion layout transformer, called DLT, where we apply the diffusion process jointly on both the continuous and the discrete features. The framework has a flexible conditioning mechanism that allows our users to condition on any given subset of all the attributes of the components, like their classes, their locations, and sizes. And most importantly, it achieves state-of-the-art results on a variety of datasets. At the high level, our architecture is based on a transformer encoder. The encoder takes embeddings of components and the current timestamp t and outputs the cleaned coordinates and the classes of the components. Our layout diffusion process is obtained by sampling all component attributes from the data distribution. We apply a continuous diffusion process on the continuous attributes and independently apply a discrete diffusion process on the discrete attributes. We then train the model with a combined loss that includes both the discrete part and the continuous part. The embedding of a component is the concatenation of the embeddings of the position, of the size, and the class. In each of these sub-embeddings, we include a conditioning mask, which allows us to explicitly inform the model which attributes are generated from the diffusion process or from the conditioning information. This allows us to optimize the conditioning scenarios not only during inference, but also during training. This really enhances the performance of the model. During inference, the output of step t is noised back to step t-1. We then repeat this process multiple times till we get the final results. So here we can see examples of the diffusion process on 3 common conditioning settings. The example in the left shows the unconditional setting. Here we specify the total number of components, and the model simply generates the layout from scratch. In the middle example, we specify the types of components we have and ask the model to generate the positions and sizes of the components. And finally, in the right example, we specify the size of the components and the model just positions them. We evaluated the performance of the model on 3 popular layout datasets of diverse graphic design tasks and using several common metrics. We see that our model outperforms state-of-the-art layout generation models on layout synthesis and editing tasks while maintaining runtime complexity that is on par with previous works. So to summarize, in this work, we introduce a new framework for a joint discrete continuous diffusion model, which includes a flexible conditioning mechanism. Furthermore, our framework can be easily extended to support additional layout features like the component colors and their content. And finally, our model can be incorporated into a wide range of mixed generative tasks like multimodal generative tasks. So if you're interested in more details, check out our project page given here. Thank you.